So now let us move on the CI interval for CI for proportion. Okay. So again, we have notation and sample size, P sample proportion, X the number of success total in sample, which we have the probability we want, right? We're looking at P hat equal X by N, P population proportion, and this standard normal distribution. Okay. So we're interested in the unknown truth, right? About the proportion of the population P. And then we use the interval to infer P, right? So we recall we have is a P has subtract plus E, right? But how we obtain the E here, the error here. So this E, we look at this theorem, A2, okay? So this theorem, we have like, if you have n observation, x1 to n randomly draw from population. And if we have some requirement 3 star and satisfy, okay? And then we can construct the 1 alpha times 100% CI to estimate the unknown truth P. P has subtract E to P hat plus E, and here P hat E obtained by this fashion. Z1 alpha by 2 times square root P has 1 subtract P hat by N. And the requirements 3 star again, it always require we have a simple random procedure. And basically just help to guarantee that all sample type N, they get the same chance of getting chosen, right? And so which means we don't have any intention purpose when we get the data, right? A sample size less than 5% population size. And here you have like a kind of success or failure, right? People have that property or not, right? Another condition to make a good estimation is that like n times p hat 1 subtract p hat greater than or equal to 10. So this condition is a help to get a close approximate. So here like Tennessee Union vote, survey 300 Tennessee Union members. We didn't know by TUM. 190 favor the Republican candidate for governor. Construct a 95 confidence interval for population proportion of all TUM favor the Republican candidate. Interpret the result, and then construct a 99% confidence interval for the population proportion of all TUM favor the candidate. Which CI is larger? And does it make sense? So first, we need to check requirement 3 star. So 3 star is required that sample symbol random sample is satisfied, right? Often is a typical standard. Now sample size less than 5% population size. So 300, it should be less than 5% of the TUM. Okay, you can check, but the TUM I believe is much larger than this one cannot be at most at 5% of the TUM here. And then the third condition, which is the condition where people either favor or not favor, right? Favor against, right? And also the last condition, which is n times p hat 1 minus p hat greater than 10 equal to 10. Okay, so you use like 300, right? Time for a good approximate here. Time p hat, which is 190 divided by 300. And it's 1 subtract 180 divided by 300. Okay, it should give you a number bigger than 10. We can check it now here too. Time 190 divided by 300 time 1 subtract 190 by 300. Okay, so this will give you a good estimation, a good approximation. Okay, so given all of that, now we construct a 95% confidence interval first by using this formula, right? P has subtract plus E, and E calculated by this way. Okay, Z1 alpha by 2 times this quantity. So for our problem here, because we talk in part A, we talk about 95% confidence interval. So which means alpha significant level is 5.05. So this value is z of 975, and you plug in inward norm function in your TI, it will give you 196, and from that you can get the error, right? Error, which is z1 alpha by 2 times square root of p hat 1 subtract p hat by n. And then remember, square root of the whole, okay? A lot of time I see you make the mistake by put the n outside, and it will cause you make the error in calculation for e, and which means it's give you the error for the whole calculation, right? If you do manually, okay? So in this case, you get an error 0.055, and from that you can plug in and you can get this interval, okay? 0.578 to 688. So interpretation here is that we are 95% confident that this interval from 0.578 to 688 here capture the true proportion of TUM in favor of the new candidate, right? The candidate. And in part B, you construct a 99% confidence interval. So everything is the same, right? The same, but the alpha change from 0.05 here to 0.01. So because alpha changed, so the critical value here also changed to 0.995 instead of 0.975 here. And you do inward norm function, it will give you like 2.576 here, and plug in as the same as above, you get the error 8.072. So which means at that time your 99% confidence interval would be 0.561 to 0.705. So but C is which confidence interval larger, it makes sense or not, right? So in this case, you can see the interval for a 95% interval is from 578 to 688, okay? So we say that, okay, with 95% confident that the true proportion of people in favor of the candidate is from 0.578 to 0.68, right? Which is about 7.8% to 68.8% in favor of the candidate, right? We're 95% confident. And in part B, we say we are 99% confident. So we're more confident that the true proportion belong to about 0.561 to 0.705, which means we're 99% confident that the true proportion belong to about 56.1% to 70.5%. And you see that part B, we have larger interval, right? So the interval part B is cover interval part A. And it doesn't make sense, right? Because in part B, you're more confident. You're about 99% confident. But part A, you're only 95% confident. So which means like a trade-off here that you're more confident, but you also have to pay the price here that your interval has to be larger, be enlarged. And the good news, again, you also can find it by using the TI, and I would recommend use your TI calculator in your test. Okay, this way you will avoid and the mistake as much as you can given the time constraint. So what you need is that you use start test and then run proportion the interval. You insert the x, the number of successes, the n, the sample size, and the confidence level from the alpha here. In the case you have process data, right? Which means you have given the p hat, and then you have to recover the x. Okay, and you need to do a little bit more labor by recover the x equal n times p hat, and you round to the nearest integer. Okay. 0.5 or above, you round up. 0.5 below 0.5, right? You round down. So now we can also look at the TUM example, right? By look at the 95 and 99 confidence interval, right? Percent confidence interval. So for part A, you do start here, you test, and you do one proportional interval, one proportional z here, option 5. Oh, no, test interval. I'm sorry. So which is the option way below here? A, okay, A. So you're actually 190 because 190 people have favor the candidate, right? Yeah, and sample size 300. And the interval level you want 595, right? Can you calculate? So you go to 5, 7, 8, 6, 8, 7. Right? So this is what we'll have, right? This is what we got here. I think there's some small error here, but anyway, it's at 1,000 digits, so it shouldn't be a problem here. Because here we round up from a calculator, it'd be 79, right? 5, 7, 9. But anyway, okay. So here 99%, right? 99%. How about 99? You change a little bit here. One proportion option A, but you move to 99, right? Which is 561 or 62, right? You round up. So this is 705. Okay. Okay. I think there's still maybe some small error in terms of round up thing. Okay. From the KI exactly is maybe more accurate because here we do have some kind of rounding and it cause some error here probably. But the DI is plugged in directly from a procedure, so it should be more accurate, I believe. Okay, so see here. Now we move to sample size problem. Okay, so this is also a very important problem because a lot of time, people they survey data, right? And they wonder how much data I should need, right? If I take a lot of data, it's good, but it will time consuming and it's costly. If I don't have enough data and maybe, when I do the inference, my procedure may not valid, right? So basically a lot of time people, they will run to the statistician to ask for advice, right? About the data collecting procedure. So here, we talk about the sample size problem for the estimating proportion. Okay, we have a similar version for mean, but for this class, we just constrain ourselves here. So before collecting data, one important practice is that finding sample size to save costs, right? So here, the good sample size required to estimate the population proportion is decided by this fashion. If, say, previous study, we have some reliable p-hat already, and now we try to conduct a new study, to see, the trend. And then your sample size you needed will be the cell of Z1 alpha by 2 square times p-hat, 1 minus p-hat divided by E square, error square, okay? This is a sample size 1. And remember the cell value is just a closed integer that at least x, right? From x number above. And if nothing know about p-hat, which is you cannot find any reliable p-hat ahead of time, and then you just choose the p-hat 0.5. I think it's fair, right? Because p from 0 to 1, so just do 0.5, which you don't know. At that time, you use the formula above, but you plug in p-hat 0.5, which means it will give you the 0.25 in the numerator, right? So it would be z 1 alpha by 2 square times 0.25 divided by e square, error square. So this example about online flower shop here. So say you plan to open an online flower shop, right? And to learn about proportion of people in favor of the idea, right? That online flower shopping. How many people need to survey to be 98% confident that the margin error, which is the E, right? No more than 2% given the following, which is no more than 0.02. So there are two scenarios. Either a recent study suggests that 70% people in favor. Okay, so you get some BS estimation from somewhere, a reliable resource. And then in the part B, no additional information available. So this happen a lot of time when you do something really new, right? And you don't have information available. And any talk when you look at result A and B, so you have to finish A and B before you can move to C, right? So in A, when you have p-hat reliable available to you follow the first track here. N equal to z1 alpha by 2 square times this. So here the error at most is 0.02, the p-hat available is 0.7, right? And you want to be 98% confident, right? About your result, your estimation. Sometimes basically alpha at 0.02, and you can get the z1, the critical value here is 2.326. And which means your n here, you plug in, right? And you get this, and you get 2A41. 2A41 is a sample size needed. So you calculate, you get a 2A40 and 0.395, and you round up a little bit, you get 2A41, right? And then no information available, so you get the n here. Other time, basically, your pH, you just put 0.5, right? A safe bet, right? So basically here, and you get this much, so you get 3382 with sample size you need. So from A and B, you can see that when you get for the same goal, right? So your goal here, you want to be 98% confident, right? And you don't want the margin error go more than 2%. But if you have some reliable study available to you, and then the sample size needed will be smaller, right? So we shrink about 500 observations. So it's just still a big deal, right? You save you a lot of time and effort. So here the conclusion here, same goal, sample size need smaller, right? If additional information available. So let us look at this quiz 831. For financial purpose, it's important to estimate the percentage of full-time college students who earn a bachelor degree in 4 years or less. Find the minimum sample size needed such that the maximum error is 0.03 and confidence level is 99%. Assume that prior study have shown that about 55% of full-time college students who earn a bachelor degree in 4 years or less. So this is a sample size problem. So do we know anything about p-hat from some source, right? So here they say like prior studies shown that 55%, right? Of full-time college students who earn bachelor degree for years less. So which means in this case, your p-hat is none, which is p-hat equal to 0.55, right? 0.55. And you have to go with this track, the first track. Z1 minus alpha by 2 square times p-hat, 1 minus p-hat is square, right? And error here 0.03, you got it, right? The p-hat is 0.55. And what remaining is a critical value 0 and alpha by 2. So in this case, alpha is 0.01 because the confidence level you look at is 99%, alpha 0.01. So the z1 alpha by 2, which is the z of 0.995, right? 0.995. So first thing first, you need to calculate your z 0.995. I believe we do have that calculation here. So 99% here in this case 0.995, 2576, 2576 for, so we don't need to repeat it, the calculation here, 2576. So we plug in this track 2576 square here, right? So 2576, right? That we got, right? 2576 from the here. Square time p has one subtract p hat, right? 0.55, 0.45. So it's 0.55, 0.45, and divide by the sample size, which in this case you got, I'm sorry, divide by error. But remember, you have to square the error, okay? A lot of time I see you make mistake by forgetting the square here, and it come to the wrong answer, okay? Wrong answer. So let's check everything here. Good. We should be fine now. So 1824 on 8, and you sell it, right? Which is 1825. So this 1825, right? 1825 students, right? 1825. So we ended the chapter here, and thank you so much for your attention.